this computer. All right. So one way to look at this material that's coming up is we've been working this whole semester just to get, this is the culmination of everything we've done so far. Because in chapters 8, which will be one exam, and then chapter 9 will be another exam, they're both dealing with chemical bonding. And everything about chemistry has to do with the bond. When you think chemistry, you ought to instantly think the bond. And it's really a modern concept, the chemical bond. And it goes to the root of why substances change from one thing to another. Of course, the question, why do atoms bond with each other, has been around for quite a while, as long as the concept of the atom was there. The question was, how do they interact? How do they form these bonds and produce the different compounds that we see? Well, it's not a simple answer. In fact, there are several theories that have sprung up over the years, and each one does a pretty good job as long as it's limited. In other words, you remember when you have a theory and your theory goes wrong, what are your choices? If your theory doesn't
Change something, try again.
right, modify it.
Yeah.
Yep, that's one.
Scrap the whole thing.
Right. Start over, and then one other. Modify, start over, or no, restrict. Restrict its application. You know your boundaries on this theory, so you say outside those boundaries, can't use it. Right. Good example of that, it's not chemistry, but a good example nevertheless, is classical physics versus relativity. Right. We know that classical physics works within these boundaries of size, mass. Relativity works, and velocity. And relativity works when you get to huge masses, very high velocities. And on the other end, quantum physics works. But classical physics works in the middle. So a similar state of affairs has developed over the years with concepts of chemical bond. And we're going to talk about them. We're going to take them more or less in chronological developmental order, so that because that's the best way to approach them. The first concepts worked okay for this, and then we tweaked them some, and then we got better, and then we had to change completely. So it's a neat little story. But a chemical bond deals with, first of all, the forces that hold atoms together. I mean, if it weren't an advantage to be held together, they wouldn't be together. You know, it's kind of like dating and marriage. if it's not working, you don't stay together, right? Here's a very good general concept to hold. A bond will form if the energies of the products are lower than the energies of the reactants, or the separated atoms. So, for example, if you have, say, that atom and that atom, and they're going to form a bond, then the energy on this side must be less than the energy on that side. Right? Chemical reactions tend toward lower energy levels. Now, that being said, a lower energy level, if we draw a diagram, this is the reaction progress from left to right. The reaction is proceeding that way, and this is the energy level. Well, if both of them together start out at this level, then you would expect them to end up over here somewhere, like that. That's a bad choice of sign. This is a bond, not minus. That's a bond. Okay. So how they get there is irrelevant, unless there are intermediate products that are also stable. So if you go up here like that, you might find a stable position in there for something else to form. Right? So when we say the bond will form if the energy of the aggregate is lower than that of the separated atoms, that's a localized effect. Now, if on a test, that's the only information you're given is here and here, of course, you draw your conclusions based on that concept. Okay, so what happens when two atoms come together? Sometimes. Let's be more basic than that. When they approach, what do they see? You know, anthropomorphize a little bit. What does each atom see as it approaches the other? Does it see the nucleus? No, it sees the electron cloud around the atom. Now, of course, the way that electron cloud is positioned, where it is in various orbitals, is dependent upon how many electrons there are, how many protons there are, how they arrange themselves. We've gone through that last chapter. But that's the first thing they see. That's where they interact with their electrons, right? And the orbitals that they occupy. So you can think of it, actually it's good to think of it both ways. The electron probabilities intermingling, and it's another way of saying the orbitals overlap. Now this is a representation of two hydrogen atoms as they approach. Right? We start to get probabilities of finding electrons starting to concentrate between the atoms and not so much on the outer peripheries of the atoms. And then when the bond is finally formed, the highest probability of finding electron density in this molecule is between the atoms. At that point, you have a bond. Okay? And you can use that model with any of the diatomics. Hydrogen, nitrogen, oxygen, fluorine, chlorine, bromine, iodine, any one of those, we could substitute in there and see the development of that bond. Now, there would be some particulars that vary, right? Because you're dealing with different orbitals here. As you move down, the higher level, the valence electrons are further away. So there are differences in the strength of the bond, for one thing. But the basic concept is there. Now, if we look at this diagram, it's similar to the one I just put up here, except that this axis is the distance between the nuclei of the two atoms as they approach. It's best to look at this diagram not from left to right as we would normally do, but from right to left. Because right to left says these two hydrogen atoms are separated, right? So the potential energy between the two is level for a while. As they get closer and closer and closer, they start to form the bond and they reach a low energy, a trough, if you will. And the lower energy state is desirable. I mean, you've heard the universe is running down. You've heard that? No. You will. Stick with me and you'll hear it loud and clear. But the concept is that energy flows from a high level to a low level. It's going to do it whether you like it or not. And what we try to do is intercept it so we can use it on the way down. Okay. But what's happening here is that these atoms prefer the lowest possible energy level. That's where you have as close as they're going to get, and the strongest bond they're going to have is at that distance, 0.074 nanometers, or 74 picometers. If you try to push them any closer, they resist, right? So why are they resisting?
The electrons will push each other apart.
Okay, you got the density in here for your bond. That's your ideal. Right? You got a proton here and a proton here, and this electron probability in between. Right? So when you try to push them together, now what are they seeing? They're starting to see their nuclei. And not only are the electrons don't have room to operate in that region, you're seeing the repulsive force of the protons. So as you push them together, they resist.
That's why the energy level goes.
And the energy level just goes through the roof. And that's why, well, one of the reasons that I can think of at the moment, why cold fusion won't happen. Right? The sun fuses hydrogen together and makes helium. And when it does that, some of the mass of the two hydrogen atoms is converted into energy, you know, based on Einstein's equation. That's where all that energy comes from. Well, the sun can do it because it's both hot and dense. So at the core of the sun, you've got these massive forces that are pushing these atoms together and overcoming those repulsive forces. Plus the high energy is forcing them to slam into each other at extremely high energy levels, high velocities. And then you reach a certain point where the nuclei fuse. And that's when they give off some of their mass as energy. But we're not talking about that now. We're talking about chemistry. And chemistry is the formation of these bonds. We're not talking about nuclear physics. But I was just carrying the point to the absurd limit. Okay. A couple of terms that you need to become familiar with. And this goes back to your original idea where electrons are transferred. Sometimes that does happen. And when the electron, one or more electrons is completely transferred from one atom to the other, you develop an ionic bond. This usually happens between a metal. Actually, it always happens between a metal and a non-metal. Okay, so somebody from over this side, somebody from over this side, come into contact. And these guys just love to give up their electrons. And these guys just love to receive them. So an example is, say, sodium, which is an alkali metal, and chlorine, which is a halogen. Right? So, well, let's be accurate here. Chlorine is diatomic, right? And sodium is a metal, chlorine is a gas. And when they get together, this one gives up an electron to that one. Actually, to balance it, you need two of these. So actually, in this case, balanced equation is 2 electrons are given up. This one receives the electrons, this one is poor in electrons by 1. And now you have an ionic bond.
Sodium chloride.
Huh?
Is it sodium?
Sodium chloride, table salt. Okay, the other possibility is where the electrons are not given up completely but shared. We call that a covalent bond. Okay, covalent bonds usually form between 2 nonmetals, a non and a non. For instance, let's see, try to find a simple one at the beginning. Oh, well, any of these diatomics that we talked about earlier would be covalent bonds. Those hydrogen atoms are sharing an electron between them. Actually, 2 electrons. 1 electron from here, 1 electron from here. Anytime you see a single line, that's 2 electrons. A bond is always 2 electrons. So if we had something like oxygen, oxygen shares 4 electrons between them, right? So 2 and 2. And nitrogen shares 3. Okay, I'm jumping ahead a little bit, but stream of consciousness. So those electrons are shared. And these things don't exist without that sharing. Whereas an ionic bond, you can have sodium ions. Once you form a sodium ion, you know, sky's the limit. It can go anywhere it wants to. If there are chlorides nearby, okay, sure, it's going to associate with those. But if you throw this salt crystal in water, what's it going to do? It's going to get ripped apart by water molecules. They're going to come in here and like that. So those ions still exist. It's just they're not solid anymore. Right? You have a solution in that example. But these are intact molecules, right? They're all gases. And you can mix them together and they'll form a solution. Like nitrogen and oxygen is what we breathe, forms a solution. But they don't interact with one another. I mean, they don't swap bonds. Okay? They're intact molecules. That's characteristic of covalently bonded compounds. And under some circumstances, they will react. And I'm not saying they exist that way forever. If they did, then we'd have a really hard time making food, growing crops. Because the nitrogen in air is the primary source of nitrogen for legumes, for instance. Anybody ever, probably never done this. Grab a legume and yank it up by its roots. Like clover, soybeans, well, even some trees, but they'd be a little harder to get out of the ground. But on their roots, there are nodules. If you cut into those nodules and they're active, they'll be pink. Okay? And what are they doing? They're taking nitrogen from the air, and the symbiotic bacteria in the nodules are taking that nitrogen, converting it into what we call fixed nitrogen. This usually starts off as ammonia or ammonium ion, and it could be converted to nitrate in the process too. But that makes the nitrogen available to the plant. The plant doesn't have the enzyme systems to convert nitrogen from the air into usable nitrogen that they can put into its structure of proteins and nucleic acids. But the bacteria do. So they form a nice little friendship. For other crops that don't have that ability and don't have symbiotes in their roots, we have to supply the nitrogen for them. One way that they get it is through decomposition of organic material in the soil. The other way is we provide it as a fertilizer, right? And the primary source of nitrogen, fertilizer, is nitrogen gas from the air. You combine it with hydrogen, and you make ammonia. 3. Actually, that's a liquid. This is the Haber-Bosch process. Takes nitrogen, makes ammonia. We use it for fertilizer now. That's not balanced yet. Let's see. 2 and 3. Yeah, now it's balanced. But originally it was developed to make explosives. You know, Haber was a good German, World War I, and the Allies had cut off the German supply from Chile, which was bird guano. It was just loaded with nitrates, and they turned it into explosives. Well, Haber came up with this procedure where he converted nitrogen from the air using hydrogen from any source, made ammonia. And ammonia, from that step, it's easy to oxidize it and make nitrates. Then you can make your explosives. Or you can make ammonium nitrate, which is also a good explosive. You add a little fuel oil, and then a blasting cap or a stick of dynamite, and you knock down the Alpha P. Murrah building in Oklahoma City. But what I'm saying is, these are intact molecules with their bonds. And they don't interact unless the conditions are right. If you just put them in a container, you can wait for centuries and then nothing will ever happen. Right? You need the right conditions. So that was the trick that Haber came up with, and then Bosch refined it. You know, Bosch and Lomb eyeglasses, optical equipment. You've heard of them? Okay, that's where they got started. Okay, so basic difference between ionic and covalent bonds. Transfer completely or just share. There are intermediate cases, right? This is a situation where we try to understand the bond, and in doing that, we try to pigeonhole various bonds. And at one end, we have ionic, at the other end, we have pure covalent, and in between, we have a continuum. So it's fair to say that every covalent bond has a certain ionic character. You know, it's not complete, but it can be measured and quantified as a certain ionic character. It could be as little as 1%. So in this continuum now, we have covalent bonds in which the sharing is not equal, right? One side might grab a little bit more electron density than the other, right? Perfect example of that is what? Water, right? Oxygen has a much stronger pull on electrons than hydrogen does. So the density in this bond is going to be more up here than it is toward the hydrogen, right? That's a polar bond. It's a polar covalent bond, right? Now, what would be a non-polar covalent bond? In other words, one where the distribution was equal. Something like that. We got the same type of atom, same element on both sides. They're pulling equally, right? That's guaranteed to be nonpolar. Okay. Oops, I went backwards. Polar covalent. Yeah, sometimes we, no, I'll get to it later. I don't want to give you too much ahead. Let's try to stick with the slides for a minute. So, how can we determine the polarity of bond? Well, you have some very sensitive instruments that basically, and this is a schematic view, you can put, in this case, hydrogen and fluorine together. Fluorine has a stronger attraction for electrons. In fact, fluorine has the strongest attraction for electrons of all the elements. And when you form the compound hydrogen fluoride together, and this is not hydrofluoric acid, this is hydrogen fluoride gas. And you put it between these two plates and you charge the plates, and you know exactly what their charges are. So you know the strength of the field. And the presence of these molecules in that field changes the output. You can measure it and correlate that to the polarity of the bond, right? And I guess they're showing you already. These little squigglies, that's the Greek delta. Right? Capital delta is this, right? Because it looks like a delta, right? From a river, well, they call it delta. But this is the small delta. Capital letter, small letter. And we use the small letter in this case to represent a slight charge, not a complete charge, as you would have with a one electron sitting by itself or one proton sitting by itself. It's just a slight charge to show that there is a difference. So the negative side is going to be on the fluorine side, and the positive side is going to be on the hydrogen side. Okay. All right. So this is just a review. What do we mean by the chemical bond? It can be described as a force that holds atoms together and makes them function as a unit. So why do atoms bond with each other to form molecules? Well, there are several explanations, but the one we've gotten so far is they bond because the energy of the aggregate together is less than the energy of the atoms before. They want the lowest possible energy state. And how do they form? Well, they could be complete separation of charge, positives over here and negatives over there, or they could be sharing, could be ionic or covalent. Okay, now we talked about the strength of pull by an atom on electrons. There's a name for that. It's called electronegativity. How strong does an atom pull on an electron? This concept was not really new. It was proposed by Berzelius in the early 19th century. Remember who Berzelius was? He's the one that gave us the system of symbols. And he proposed that system that we have today. And thank God he won, because some of the others that they were proposed were really, I think that's bad. Other chemists had investigated this concept. Avogadro was one of them, right? So they might be famous for one thing, like Boyle for something, and Avogadro, you might think of him for something else, but they branched out. Right? They just happened to hit on something that was noteworthy, right? And attached their names to it. But they were active in many different fields, especially back in this era when you had, I don't know what you call them, natural philosophers, I think was the term they used. we would call them maybe today polymaths. They delve into everything. Newton was fond of alchemy. He'd been perfectly happy to convert lead into gold if he could. Oops. The one I want to focus on, his name is Linus Pauling. He was a chemist, a chemical engineer, a biochemist. He was a lot of things. He was born in 1901 and lived into his early 90s. I think he passed away from prostate cancer. But he's also known, you may have heard of him, as the mega vitamin C taker. He said, everyone should take mega doses of vitamin C. And he based that upon the fact that vitamin C is a very effective antioxidant. Various compounds that float around in your body, various atoms, small molecules, have a tendency to damage your genetic material if they're left on their own. And antioxidants neutralize those. Right, that's the short version. And since being a biochemist, he reasoned that this very effective antioxidant, vitamin C, which is found in nature and in our food supply already, but could be produced in pure form as ascorbic acid, actually a certain type of ascorbic acid called L plus ascorbic acid. That's vitamin C. So he would take mega doses of it, and who knows? I mean, it could have prolonged his life. Maybe it did, maybe it didn't. Because anybody had statistics here? No, you don't know what degrees of freedom then is. Degrees of freedom is the sample size minus 1 is degrees of freedom. And it's an indication of how reliable your data is. Right? The bigger this number, the more reliable, because you have a larger sample size. So Linus Pauling's degrees of freedom were 0. There's no way to calculate a mean with one sample, right? Okay. So we really don't know. But that's not what I want to focus on here. He was really a very brilliant chemist. And he spent his life focused on the nature of the chemical bond. In fact, he wrote a textbook on it, and he received the 1954 Nobel Prize in Chemistry for his work in making sense of the chemical bond. In sciences, there are two things you can do. You can divide science up into two types of investigation. One is analysis. That's where you take the information you have and you break it apart, try to figure out what it says. Right? The other is synthesis. And that's a much more difficult process. It takes a real spark of genius to synthesize lots of different information into a coherent model theory. And that's what Pauling did with the information that was available on the chemical bond. He was a synthesizer. He did analytical work too, but he brought everything together in a coherent package and instructed us on the chemical bond. Now, he wasn't the final word. I mean, he was a stepping stone. He was also the only person I can think of right now who got 2 Nobel Prizes, but only one was in the sciences. The other was a Peace Prize. Later in life, he became active, and he received the 1962 Nobel Peace Prize for his activities against nuclear proliferation. So he actually did something to earn his Peace Prize. You know, it's not like our late president. I don't know why he got that one. You know what I'm talking about. His last name starts with an O. Anyway, so several scientists had proposed measuring and presenting electronegativity, the strength of attraction for electrons, for each of the elements on the periodic table. And the reason they wanted to do that was they thought that if they knew how strongly each element attracted electrons, they could deduce some things about bonds that might form between two or more of them. Okay? So this is just, this is not really the equation he used, but it sort of gives you an idea. If you have, you compare the expected bond energy for this element and that element, and then you take the bond energy of that element bonded with itself and that element bonded with itself, add them together and divide by 2, then that's what we expect would be the bond energy here. That, like I said, that's oversimplified. I don't think I could even follow his math. But he came up with a simple number scheme, right? And it went from very low, right, fractions less than 1 over here, up to about 4 for fluorine. So you have that range. And if you subtract one from the other, it gives you a rough idea of what's the ionic character of the bond. Should it be covalent? Should it be ionic? Or should it be somewhere in between? Okay. Let's see. So that the element that has the higher number, the larger number, is the one that's going to draw electrons to itself the strongest. So if you have something like maybe sulfur bonded with I don't know, calcium. Right? You have calcium like that, and maybe probably 2 bonds. Anyway, we can be fairly certain that it's going to be ionic, but we don't know how ionic. Right? We don't know what character it has until we compare the numbers, the electronegativity numbers. Right? So this one's going to be larger than this one because it's over on this side. So we subtract this one from that one, and it gives us a number, and we can make some conclusions, draw some conclusions about the character of the bond. Oops. Go back. Okay. So, trends. What kind of trend does electronegativity show in the table? I sort of gave it to you already. As you go up a group, the electronegativity increases. The attraction for electrons increases. And as you go from left to right, the attraction increases. So taken together, lower left to upper right, you should get an increasing electronegativity. Now, they do so for different reasons. Within a group, the electronegativity increases because the electrons are in orbitals that are closer to the nucleus. So the attraction is much stronger. Okay. As you go from left to right, you're adding protons, and that's drawing the electrons closer. In combination, lower left, up right, you get both of those combined, you end up with fluorine as a very small atom, but one that has sufficient number of protons to really grab hold of electrons. I mean, just, it's like tiger claw for plumbers. Isn't that what it's called? You put those connectors, put your pieces of pipe together, and they're stuck.
Oh, yeah, they won't come back up.
Isn't that what it's called? Tiger claw?
Yeah.
It's a lot easier than soldering. Anyway, So that's the trend for electronegativity. And Pauling scale, sometimes they, if you round it off to just two significant figures, see how it's 4.0. But if you have three significant figures, it's usually reported as 3.99 or 98. But it is the highest electronegativity on the table, and the lowest is cesium. Now, why is it francium? Because it's radioactive. It takes a little more time to do this measurement than the half-life of francium, so we just kind of, we leave the radioactive ones out. Okay, so this is a generalized picture, a false three-dimensional picture of electronegativities. And as a general trend, from lower left to upper right, you do see an increase. But there are some inconsistencies here. Right? You'll see them occur right in here. And let's see, that's the biggest ones. I was expecting to see one over here, but I guess that's not, no, this is it. So the inconsistencies happen in the transition metals. Okay, so let's see if we can make sense of this. Use what we know. If lithium and fluorine react, right, so let's find out where they are. Lithium's over here. My apologies to the viewing public. Lithium's on the far left-hand side. Fluorine's over here on the right-hand side. So which one has more attraction for the electron?
Would be fluorine.
Yep, fluorine. Yep, and in the bond that forms, well, let's see, I skipped ahead too far. So fluorine would have the stronger attraction for an electron. Why is that? Well, they're in the same period. So our explanation here is simply a higher effective nuclear charge, right? More protons. In a bond between fluorine and iodine, which can occur, strange as it may seem, you can get two halogens bonded together other than the same atom, same type of atom. Fluorine and, what did it say, iodine? So who's going to have more attraction there? Fluorine, right? Because the electrons are in lower orbitals. And that exposes more of the nucleus. Makes it, they call it shielding. Right? When you surround positive charge with negative charges, the ones on the far outside, they feel some of the positive attraction, but they also see some of the repulsion from their inner neighbors. Right? So the effect of the positive is not as great for the electrons out here. They're shielded from it. So we would expect fluorine to have the higher attraction for electrons there also. We don't need to beat this horse. You know that the trend is increase this way, increase that way. Right? So this is in words, why across a period. You're increasing the number of protons, the effective nuclear charge. And the electrons don't have as much shielding effect, in fact, almost none, because they're all in the same orbital. Right? The valence electrons are in the same orbital, so you don't see the shielding effect. As you add more protons, you do get more effective nuclear charge. And this is in terms of down a group. So as you go down the group, you're adding electrons to farther from the nucleus, right? So those, and the electrons underneath are shielding the nucleus from any approaching atoms or electrons. Okay, so this is out of your book. I don't know, it may not look exactly like this because these are old slides. But it should be in chapter 8 somewhere. And if you look at the difference between electronegativity, of course, we've presented one example, which is where the elements, two elements of the same kind bonded together. That's perfectly nonpolar. So their difference would be 0. And that bond would be a pure covalent, nonpolar covalent bond. If you have a large electronegativity difference, and it's large enough, we could classify that as ionic. And this is pure ionic character versus pure covalent character. And then in between, you have some of both. Now this one, I don't remember where I got this chart, but I was looking for, you know, if you have absolute numbers, can we use those to tell us what's the character? It's generally accepted in this case that if you have less than 0.2 difference in their electronegativities, you're talking about nonpolar covalent. Right? So if we look at, let's go back. Here we go. If we look at a difference between hydrogen and boron, that's 0.1 difference. That's definitely nonpolar covalent. And a common boron compound is boron trihydride. And that's nonpolar covalent bonds between boron and hydrogen. If we had something that's greater than 2, right, say oxygen, greater than 0.2, excuse me. Oxygen and carbon, right, what is that, 2.5, 3.5, so that's 1. That would be a polar covalent bond, like for carbon dioxide. Polar covalent. And of course, we talked about, let's see, hydrogen and fluorine would be, what, 1.9? So let's look. Here we go. Greater than 1.9 is ionic. So that HF bond is considered ionic. Polar covalent, somewhere between here, 0.3 to 1.4. So that would characterize polar covalent. So that gives you a general idea. So let's see if we can arrange these in order of most to least polar. Now, it doesn't say that they're covalent. So if they happen to be ionic, okay, we can say, yeah, that's really polar. So for A, we've got nitrogen and fluorine. We've got oxygen and fluorine. And we've got carbon and fluorine. That's good, because we're comparing apples and apples. Everything's compared based on fluorine. So you just need to know the difference between nitrogen, fluorine, oxygen, carbon. So we just look at the chart. We just look at the periodic table and say, let's see, here's carbon, nitrogen, oxygen, fluorine. So the most polar is going to be the one furthest away, right? It's going to have the greatest difference in. So the most polar is carbon. And then this one is second, and this one's third. Carbon, nitrogen, oxygen. Okay, how about this one? CF, NO, and silicon and fluorine. Now we're just talking about individual bonds here. These are not compounds necessarily. Okay. We're just looking at the individual bonds. So, which one is the farthest away? Let's see. There's carbon and fluorine. Right? Nitrogen and oxygen are really close together. and silicon and fluorine, right? So there's carbon in fluorine, but silicon's down here, lower to the left. So silicon and fluorine should be the most polar. The next polar should be carbon and fluorine, and then the least, nitrogen and oxygen, because they're the closest together. Okay, last one. That's obviously nonpolar, right? And then boron and chlorine, and sulfur and chlorine. Okay? So this is going to be the last one. We know that because they're equal elements. How about boron and sulfur? Boron and sulfur. That's tricky. We should see these two are really close together, so I would expect them to be number 2, and this should be number 1. This would be the most polar. That would be next, simply because sulfur and chlorine are very close together. And let's see. Okay. That makes sense to everybody? Okay. All right. Let's see how we're doing. 30. Okay. So here's a question that is conditional. We want to know which will be the least polar, yet still be considered polar covalent. Right? So what we need to do is eliminate those that are ionic, because that's not covalent, and those that are pure nonpolar. Right? So let's see, magnesium and oxygen. Magnesium's here, oxygen's over there. That's ionic. So we throw that one out. And then let's see, oxygen. That's pure nonpolar covalent. So we throw that one out. Now we only have to compare carbon oxygen, silicon oxygen, and nitrogen oxygen. So there's carbon, nitrogen, silicon. And the least polar would be the one that's closest to oxygen, NO. Okay? Pay no attention to the wizard behind the curtain. Okay, so that's sort of a test-taking technique. You eliminate the answers that don't satisfy the conditions at all. Then you go for the question that it's asking. What is the least polar? Okay. Oh, we got another one. Which of the following would be the most polar without being considered ionic? Well, the most polar without being, this is ionic, so we got to throw that one out. Of course, oxygen doesn't count because it's nonpolar. So again, we're looking for the other end of the spectrum. So we want the ones that are farthest away from each other. There's carbon, oxygen is distant, but silicon is down here, right? So with our trend, left to right, top to bottom, silicon and oxygen should be the answer to that one. Okay, I'm going to throw another concept at you. It's called the dipole moment. It's fancy words. And it's a way, actually it's a measurement that can be made for molecules and in some cases bonds that shows, that quantifies exactly how polar the bond is. And that dipole moment is a value. Now we can use that value when we construct a molecule. We'll go back to water again. we determined that oxygen is more electronegative than hydrogen. Right? So it's going to have slightly negative charge. And then hydrogens are going to have the slight positive charges. And to be consistent, probably ought to have two of those. But the dipole moment for the bond is in the direction of oxygen. And we indicate that with an arrow, with a plus tail on it to show the positive end, and that's the negative end. So this one will have an arrow of equal size, but a different direction. Okay. So these dipole moments then, when we add them up, and that's it's not just arithmetic add, this is called vector addition. Right? So if you see, it's like you ever play tug of war with a rope, right? That's fun, right? Especially if you have a mud puddle in between the groups, right? The guy that's closest to the mud puddle is the one that gets it first and most. As long as you're opposite one another and you have equal strength, then it's a standoff, right? But what if you off to one side and try to pull? Then you don't get any opposition, right? The only way to balance those two is to have somebody else in a third direction pulling against you, right? So that's what the vector addition does. It says that adding those together, overall for that whole molecule, makes the overall dipole moment for this molecule that way. Okay? So each of these bonds are polar. And when we add them together, the whole molecule is now considered polar, because it has a slight negative side and a slight positive side. Okay. An example of what if you had polar bonds? That's what carbon dioxide looks like. And we know that with oxygen to the right of carbon, oxygen is going to have the higher electronegativity, and it's going to be pulling that way and this way. So there's your tug of war, opposite one another. Right? You have polar bonds. Oxygen this is a polar bond, but they cancel one another out. So overall, the molecule is nonpolar. Okay, so you have two things to consider when you're considering, is this compound polar or nonpolar? First, are the bonds polar? And second, what's the geometry? Those two factors will tell you whether the molecule is polar or nonpolar. Okay, any questions? All right. So there's an artist's rendition of the water molecule. And the polarity of the water molecule is central to its behavior. Right? They say water is the universal solvent. Well, that's sort of a stretch, because everybody knows that water doesn't dissolve oil. But many of the compounds on Earth anyway, are ionic or polar in character. So yeah, it does dissolve a lot of things, and it does so because it is polar. So when the water molecule approaches a compound, if that compound also has polarity, which way are they going to line up? Negative to positive, right? Right. And if you get enough water molecules around there with enough force, it will pull it apart, just like our sodium chloride crystal. It's called hydration. So there's your carbon dioxide molecule, and it overall is nonpolar. But it's interesting to me that you still get some electron density out here and some depletion of electron density in here. So on the microscopic level, it's not the same as if we said, all right, oxygen and oxygen. It's a different type of non-polar than carbon dioxide, because carbon dioxide is an addition non-polar, and this is polar from the ground up, a non-polar from the ground up. So that's nothing you need to lose any sleep about. It's just an observation. All right, so what types of geometries do we have? Well, here's one. Remember the one I showed you just a minute ago? Made reference to this one. Boron trihydride. That would be an example of a planar molecule with hydrogens around it. Well, we know from our electronegativities that boron should be the more electronegative. It's over here. Right? So you should see like that, like that, like that. But it's symmetrical, right? They're all pulling in the same direction, so they cancel one another out. So this molecule should be nonpolar, right? Here's another example. Well, they gave sulfur trioxide. How about carbon tetrachloride? You ever heard of carbon tetrachloride before? You may not be old enough. Okay. It used to be used as a dry cleaning agent, right? Because it's nonpolar. Carbon tetrachloride, you know what that dot means? That means that chlorine is in the back. Right? And what it does is it forms a tetrahedron, a perfect tetrahedron with chlorines at each of the apexes. Chlorine is more electronegative, right? But all four of these are pulling of the same strength and they cancel one another out. So carbon tetrachloride is a nonpolar molecule, very effective at dissolving nonpolar molecules like oils, right? That come off your skin and soil your clothes and gather dust to them. So carbon tetrachloride will dissolve those oils and take them away from your clothes without using water. That's why they call it dry cleaning, because your clothes don't get wet. But carbon tetrachloride was discovered to be a very nasty molecule, especially where the worker's health was involved. So OSHA got together with the EPA and they said, no more. You got to find something else. So they did. Problem is, you probably saw, well, if you had been around for the transition, you might have seen the cost of your dry cleaning bill go up instantly when you had to transition from the cheap carbon tetrachloride to something more expensive. Similar to freons, right? When they said you can't use this type of freon anymore. Then they had to go to more expensive alternatives, and you saw that some hit your wallet. Okay. Here's another concept that will help you decide if the compound you're trying to form is stable. And it's called the Octet Rule. We've already drawn electronic configurations for atoms, right? For instance, how about chlorine? Right. Chlorine's got 17 electrons, right? Okay, so let's draw its configuration. 2, 4, 10, need 7 more. Need 5 more. Right? So that should be 17 electrons. Now, what is argon? Well, argon's the same thing, except for what? Look where it is, right? It's just one to the right. So what does that mean? It's right. It's got one extra electron than chlorine does. So there you go. Now, how many electrons does it take to fill up p orbitals? Right, just like that, like that, like that, and it's full. Now, the other question is, which are the valence electrons for this atom? Right? They're all the same principal quantum number. Right? So that's 2, 4, 6, 8. Okay, that's the octet. For this one, it's missing one, right? So there is, theoretically speaking, there's a drive for chlorine to acquire one more electron so that it can look like argon. It wants to complete its octet. If it can complete its octet, then it's happy. Everybody wants to look like a noble gas. Right? They don't have enough protons to do it, or electrons that go with them. But if they can react with something and snag an electron in this case, there you go. Now, what's the charge on that chlorine if we give it that electron? Right? Because it's got 17 protons, but now it has 18 electrons. That's where its charge comes from. Right? But there is a drive for it to acquire that other electron just to complete its orbitals. Okay? Now, what about sodium? Sodium's 11. Right? We talked about sodium in general terms earlier. These are specifics. These say exactly why it wants to do what it does. 2, 4, 10, and there. Okay. Now, if sodium were to complete its octet the same way as chlorine does, what would it need to do? It would, if it did it the same way as chlorine, it would have to pick up 1, 2, 3, 4, 5, 6, 7 more electrons. Now, which is easier? Pick up 7 or lose 1? Lose 1, yeah. So it loses that one. And that means now, there it is, with only 10 electrons. Okay, that's why sodium loses 1 instead of gaining 7. So now what does it look like in its electronic configuration? If it loses that one, it looks like neon. So that everybody's trending toward noble gas configuration. Okay? And that's why a rule of thumb works. Octet. Complete the octet some way. Either add electrons, subtract electrons, and complete the valence octet. Okay? Then that tends to drive the reaction. So let's pick out another one, say calcium. Okay? So let's do calcium like this. Let's do the shorthand way. Remember that? Okay. Which one are we going? We go backwards, and then we have to go, oh, we ran out of period. Let's go back to the next one. Argon, right? Okay. So our shorthand would be argon, 18. And then what's the orbital on calcium? What? These are what? S's, right? So we're filling which one? 1, 2, 4s, right? Now you ask yourself again, which is easier? Add 6 more electrons to make it look like krypton? Or, actually, it would take more than that. We have to add all the D's too. So it's 16 more. So it's easier for calcium to look like argon simply by getting rid of those. Now we have calcium with a 2+ charge because we got rid of electrons. Right? Remember, the only way that a charge can develop on an atom is by a change in electrons, the balance of positive to negative. What happens if you change it by changing protons? You change, right? You don't have calcium anymore. Now, the octet rule works fine as long as you're up here, right? And down here. But once you break into this region, you're getting into d orbitals. And now the octet doesn't work anymore. Or it starts to break down. Let me put it that way. The octet is valuable for these as long as you recognize that you've got these underlying. But you'll also notice that with these, and the further down you go, you start to develop multiple charge possibilities. And that has to do with the octet in combination with d orbitals. So the d orbitals are really good for these two. How about helium? Can't use an octet for helium, right? There's not enough room for electrons. So we have a special rule for them. The Duet Rule for hydrogen and helium. So hydrogen looks like helium when it combines, right? There's your 1 electron for hydrogen, and there's your electron for that other hydrogen, right? So when they come together and form their bond, they're completing a duet, but they still look like a noble gas. Right? So that's that one case where the Duet rule substitutes for the octet. These are other possibilities I mentioned where you can develop multiple charges for these metals down in here. And the influence there is for the 2+ charges, the influence is for the s orbitals, and the 4+ charges incorporate the p orbitals. All right. So let's see what's next on the menu. This is sort of a summation. Remember what happens when 2 nonmetals react? What kind of bond do you get? Covalent, right? They're going to share electrons because they're not strong enough. There's not a difference, big enough difference in electronegativities. So they're just going to share, get along. And say each one looks like, it thinks it's a noble gas now. So carbon gets, right, 2 electrons here, 2 electrons there, 2 here, 2 here. So if carbon gets 2 electrons from that side and 2 electrons from that side, where does that put it? 1, 2, 3, 4. Thinks it looks like neon, right? How about oxygen? It gets 2 here. So it goes 1, 2. It thinks it looks like neon. So everybody's happy. They think they look like neon. Those are covalent. situations, covalent bonds. When a nonmetal and a representative group, all right, we didn't define that term yet. So what's the representative group elements? S orbitals and p orbitals. Those are representative group elements. When a nonmetal and a representative group metal, which means here or here, form a binary compound, you get an exchange of electrons to produce the noble gas configuration. Right? It just completely transfers. Whereas with the last example of carbon dioxide, you share electrons. And in sharing, you make them feel good. They look like noble gases. Now, what's an isoelectronic series? Look at the word. Start from the tail end, right? A series can be several put in a row, right? Electronic, that refers to the electrons, right? And in particular, the electronic configuration that we've drawn before. And iso, what does iso mean? Get warm. Iso is a Greek prefix that means same. The same electronic configuration. So each of these elements has the same electronic configuration. Right? So if you start with neon, what is its configuration? Well, so you've got 10 electrons, so we have 10 electrons. We go to the left to fluorine, it's only got 9. Right? So it starts out like this. But we're going to add an electron. So that makes it 6. Right? So we're starting our isoelectronics by adding electron to fluorine. What if we do oxygen? How many would oxygen need? Right? 4, 5, 6, 7, 8. We need to add 2 electrons, wouldn't we? And that makes a 2- charge. So all those things you had to memorize in the beginning, you know, how to deal with the periodic chart and how to build compounds, always +1, always +2, always -1, always -2. That's why they're always that way. Because that makes them look like a noble gas. But all these are magnesium and aluminum, 2+, 3+. So this is 13. So each one of these looks like neon because we've added or removed electrons to make it look like neon. And that tells you that's the underlying reason for those charges that they possess. Okay. Are we leaving anybody behind yet? Good? Okay. Choose an alkaline metal, an alkaline earth, a noble gas, and a halogen. So they constitute an isoelectronic series. So where would you start if you wanted to build a series that's isoelectronic and you were given these conditions? That, and that. Where would I start? I'd start with a noble gas, right? Exactly. So let's pick a noble gas. Krypton? Okay. So krypton is 36 here. And we can build krypton from argons. That seems strange. We're building a noble gas based on a noble gas. Right? So if we use this as our shorthand, then all these are going to be the same. No, we can't do that. All right, scratch that. Because we're trying to build an isoelectronic series. Everybody see my mistake? Right. I'm shutting out my isoelectronics by burying them in that form. So let's say, let's draw the series for krypton. Right. So what is it? Don't be shy. Right? Where are we at 3s2? We're right here, right? So we're still going P's, right? 3p6, 4s2, right? Now what do we do?
3D.
Right? 3d10. And then
4P6.
4p6, right? I can do that better. Okay, now, what are our possibilities for isoelectronic series with these? They need to be in the same period, don't they? Right. So an alkali metal in this period would be what? Potassium. Yep. So potassium, in order to look like that, we've got all these, let's see. Actually, we ought to put potassium on top. So how would we make, you know, that's not going to work, is it? Why? Right. If we lose an electron, we're back to argon. That won't work. So what do we have to go to?
Go the next one down.
Right. What is it? Rubidium. Yeah. 37. Now you're talking. We've got all these are the same right here, except for what?
5S1.
5s1?
Yes.
Okay. Now we can lose that one and make a positive charge. Okay. What's the other one they want? Alkaline earth. What's possible alkaline earth?
You have to go to SR.
Mm-hmm. What is SR? Strontium, right? Strontium. Okay, so strontium would have the 5s2. So when we lose that one, we get a 2+ charge. And the other one's a halogen, right? So which halogen will we use to make krypton? Hmm? Bromine. 35. So bromine is everything out to here except 4p5. Then you'd add an electron to it and make your minus charge. That's an electronic series, isoelectronic series. Now let's see. All right, they used argon. That's good. So you have another example. We used a more difficult one, I think. Okay. Let's see. we have, last chapter, we did periodic table trends. What we're trying to do now is to understand why the trends. So you remember your trends for atomic size, right? We did that one, atomic size. So which way do your atoms get bigger? Upper left, lower right, right? They get bigger that way. Which way does ionization energy go? Right. Lower left, upper right. Right. Let's see. We also had, well, we've done electronegativity. We didn't do ion radius. That's a little trickier. The reason being that when you add electrons or subtract electrons, we can talk about general trends. Oh, good, I still got it on there. We can talk about general trends for different elements. Like if we make an ion out of iodine, should its size decrease or increase? Think of what you're doing. Where's the electron going to go? Well, yeah, that's right. But think about the atom itself. Where does the electron go? It goes into the outermost orbital, right? Right. So it should increase in size, ever so slightly. What if we take one of these, say potassium? What kind of ion is it going to form? It's a positive ion, right? So if you take an electron away from it, is it going to get bigger or smaller? Exactly, smaller. Right? Because you're thinking about the electron cloud is out here. You take an electron away from it, and it just shrinks like that. Okay. So knowing these different things about the periodic table, now we can make predictions. We know how to do the electronic configurations also based on the table. I mean, we don't even have to use that that funny chart, you know, with the diagonals on it, right? You just use the periodic table, find your element, and you can build the electronic configuration based upon its position in the table because you know the orbitals that are filling, right? S orbitals fill here, D's here, P's here, F's here. You can fill the orbitals based on the periodic table structure. And you've already become fairly proficient at predicting ionic compound formulas, right? Because you know the charges that are available. Those that have fixed charges, right? What kind of binary compound is that? Type 1, 2, 3. If the metal's a fixed charge, type 1, right? It only has one. You just say sodium chloride. You don't have to put a charge for sodium, right? Because it's always the same. That's a type 1 compound. How about this one? How do we name that one? Right, where does iron come from? Here. So it has possible multiple charges, right? Type 2 compound. So it's going to be iron something oxide. There's the charge. Now, how do you figure the charge?
When you take from oxygen.
Start with oxygen, right? So it's 2 minus here, so 3 of them is 6 minus total, right? So you got to balance this one at 6 plus. So those are balanced. But you've got 2 irons. So each one would be 3 plus, right? So then, there you go. So you can predict these ionic compounds, metal, non-metal. Sometimes it's a little more difficult because you have to be given what the charge is. But if it comes from here and here and here, no problem. You've only got one possible charge. And if you're given a type 3 compound, right, like, let me see, let me use, how about this one? How would we name that? Type 3 compounds, you just say the name, how many there are. Right. That's because they're both nonmetals. Actually, technically, silicon is a metalloid. Right? But I gave you credit for either one. Right? Remember which one that was? Right. It was on this side of the line, but right up against the line. So I said, okay, technically that's a metal, but specifically it's a metalloid. Okay. So you ought to be becoming much, much better friends with the periodic table by now than when we started. Let's see. Back over here for the benefit of our video friends. So what are the factors that influence the stability and the structure of these binary ionic compounds? That's a good question. First of all, we want to know how strong is the attraction. Right? What is the strength of the attraction? Because sodium and chlorine have a certain strength of attraction. And what type of force is involved here? Electrostatic. That's it. Purely electrostatic attraction. That's an ionic bond. Would be different than, say, lithium chloride. The bond between those two would have a different strength, right? Because the lithium, right? Yeah, because the lithium has a slightly different electronegativity. So you'd have a different strength. And we can quantify that. And the term for it is lattice energy. Lattice refers to a network of positive and negative charges. That's a lattice. It's like, I don't know, I'm dating myself. When you form an arboretum, sometimes you can build these structures with cross frames of wood to give your plant something to grow on. It's a lattice. It's interwoven pieces. So how do we determine the lattice energy of a compound? Well, here's technically, this is the formula for it. The lattice energy would be the charge on one member of the compound and the charge on the other in absolute values and the distance between them. And then you have a proportionality constant. Right, so that doesn't help you much. I mean, it's just, that's the way, that's an explanation for the lattice energy. It's more useful to know how to calculate the lattice energy. So the lattice energy, let's see, I think it's on the next slide. I don't want to steal my own thunder. Yeah. So the lattice energy is what is the difference in the energy between the separated gaseous ions and the ionic solid? In other words, if we take two elements, say X and Y, right, and these are gases, right, and they produce this solid compound. Go from gas to the solid. Now, why are we starting with gas individual elements? Yeah, couldn't hear you. It's the same reason as the ionization energy, right? You don't want other things influencing the value that you're producing. Right? If we get a value measured enthalpy of this process, we want to be sure it's not contaminated with some other process. And if you go from gas straight to solid, then there's nothing in between. These are individual atoms. Now, if they started, say, let's take, for example, if this one were that wouldn't work, right? Because that's not individual atoms. It would have to be, we would have to take that one and break it apart. And that would require some energy, right? You'd have to add some energy to get there, right? So from that point to this point, then we're good with that element. For this one, depends. This is going to be the metal, so it just depends on its state. You may just simply have to vaporize it, and that would take a lot of energy. So what are the steps? All right, so let's use this example. What are the steps required for a solid metal to form an ionic lattice with a nonmetal? In this case, the nonmetal is diatomic. Right? So we can assume it's probably one of the halogens. Okay, what do you have to do first? Well, the metal is going to be solid, except for which one? Which one's not solid at room temperature? Right, mercury. Rest of them, all the other metals are solids. So we assume that this is not a mercury. So the process to going from solid to gas is endothermic, right? You've got to break that metal apart into individual gas molecules, and that takes a lot of energy. Then, in order to get them to combine, we have to ionize that metal. So a little bit more energy to ionize it. Let's see. Be sure I'm not misleading. So far, so good. So up to this point, we're putting energy in. We haven't got anything back yet. Another case, when you take the nonmetal, you've got to break the bond between those two, right? Starts off as a gas. That's okay. And then you produce one of these. So that's another endothermic. So far, we're putting money in and we're not getting anything back. But when the electron that you broke away from, here recombines with this individual gas molecule, gas atom, now you're getting some energy back, right? Remember when an electron comes from here down to your atom, what happens? Huh? Emits, right. It comes from here to here, And if that's all it does, then you get light, right? But it's an exothermic process, right? You get energy out. Remember the convention, right? The system is everything. Add energy is plus, excuse me, this would be negative. So an exothermic enthalpy is a negative number. So this exothermic process is going to give you some of your energy back, maybe a lot. And then when you combine those these two, positive ion that we formed on the previous slide, and then this one we just formed, put them together, now you're at your final product. There's your lattice, solid. And this is probably the most exothermic process in the whole scheme of things. And this is what it looks like on a table. I know you can't see this very well, but you've got one of these in your textbook. You can look at it in detail. Or you can take your printed copy with a magnifying glass and look at it. Well, what were the steps that we went through? We started where? Let's see. That's a different one. This is a different one over here. Focus on this one right here. Right. So where are we going to put energy in? Going up here like this. We're going to take this magnesium gas and this oxygen gas, and we're going to add energy. And we're eventually going to get to these two ions, magnesium 2 plus and oxygen 2 minus. So we've run through those endothermic steps all the way up here. And then when we combine these two together, we get our magnesium oxide. And I did misspeak for lattice energy. That didn't feel right to me. Lattice energy, you take the gaseous ions. So in my previous example, the gaseous ions combine to make the solid. Right. And nobody said anything. Well, I should expect it, but this is the lattice energy, going from these ions in their gaseous state to the solid. That way there's nothing in between them, between this position and that position. The only energy that you get out is based upon the attraction of these two together. The way I had it before was inaccurate because there were not ions. So if you formed the ions from them, you had to put more energy in. That was my mistake. And that's why I have PowerPoints to help me correct my mistakes. Okay. So any questions about lattice energy at this point? Okay. This is just an example. If we go from lithium solid to fluorine gas to make the lithium fluoride solid, remember when we were talking about the heat of formation? We did talk about that, didn't we? No, we didn't. Heat of formation. Is that in the second semester? All right. Well, I'll just take this one for face value. When we want to determine, yeah, this is good. Heat of formation. So what's the convention for determining the heat of formation for any compound? Right? So in this case, we have lithium fluoride. That's where you start. In its standard state, standard temperature and pressure, right? 1 atmosphere, 25 degrees centigrade. Lithium fluoride is that. In fact, they make some really nice lenses out of this stuff. It's transparent to ultraviolet light. We had one in our spectrometer, but it's high maintenance. It will become dirty really quick. So you have to take it out periodically and carefully clean it. But we didn't have any choice. We had to use it. Anyway, the formation of this compound, you have 1 mole of that compound, right? 1 here. That's it. That's where you start. Then you work backwards. All right. What does it take to make that? Well, let's see. In standard state, lithium is a solid. It's a metal. Right? Okay. What's the standard state for fluorine? Right. It's a diatomic gas. Okay. So now to balance the equation, you can't touch this. Right. Hands off. This is okay because you got 1 here and 1 here, but you've only got 1 there. So here's where we break the rules. Right. Remember previously when we balanced an equation, we wanted whole number coefficients. Right. But for this type of calculation and this reaction, we have to use a fraction. You only need 1 fluorine here, 1 lithium there. So that's why the reaction equation is written that way. Out of convention, you start from the product and work your way backwards. Okay. All right. So now the process is, how do you get from here to there? Well, what do you have to do to this first? You have to make a gas out of it, right? That's going to take some energy. Then you have to ionize it. That's going to take some energy. Still putting energy in. I'm leaving out the electrons here. This is not balanced. How about this one? What do you do with that one? Well, you break that one in 2, but since there's only half of one, you get that one, right? And then you make the ion out of it. Okay. Then you take these 2 and put them together. Right? So we've got input, input, input. Get some of it back, right? Because the electron is coming from infinity down here. So this is delta H. This is going to be positive, putting it in, positive, you're putting it in, positive, you're putting energy in, negative, you're getting some back. And then for this one, big negatives. You get a lot back. Okay. And that's what this slide and probably the next one are all about. But they're putting numbers with them, right? So I think investigating, rather than spending a lot of time on this right now, you got the gist of it, right? And you got the review of the slides. So when you go into your review document, you're going to see 1 or 2 problems like that. Right? And when we come back next week in our review, we'll hammer away at these in detail. Okay? But that's a schematic of what you've done, each of these procedures that I outlined up here. And then once you've got your numbers there, right? There's your positives. Put energy in, put energy in, put energy in, get some back and get a lot back. Then all you have to do is be sure that these all add up to make that equation, right? Hess's law. Remember, you add the individual equations together to get the final one. And as long as they do add up, then you're safe to add these together. And this would be the heat of formation for lithium fluoride. Okay? All right, I mentioned earlier that every bond except a purely covalent bond has some ionic character, right? So if you have these diatomics, they're not going to have any ionic character whatsoever because you've got equal atoms on both sides pulling electrons. But if you have any difference at all, there's going to be some ionic character that can be assigned to that bond. And it's based upon the difference in their electronegativities. Here's the way that we calculate the ionic character. The percent ionic character of a bond. What you do is you measure the dipole moment for the XY bond, and then you calculate the dipole moment based upon their electronegativities. And then ratio them times 100, and that gives you a percent. Now, I don't think I have any problems like that for you to do. I think it's really beyond this course. But this just gives you the gist of the calculation. The real test is that right there, measuring the dipole moment. That takes a real skilled technician to do that. Okay. Calculating the dipole moment, yeah, there are copious amounts of information you can draw from there. But this really takes the skill. Right. So if you do that for a living, you want to have a good technician at your side, knows how to operate the equipment. So percent ionic character for some of these representative, right? So if we get two halogens together, the electronegativity difference is very low, and the percent ionic character is very low. But if you get a metal and a non-metal, you have high electronegativity difference between them and large percent ionic character. And that just makes sense. And it roughly forms a straight line connecting like this. Or maybe it's curvilinear, as they call it, or like that. But there's an increase. All right. When I was doing my PhD research, I had one of the faculty I went to and asked him about the procedures, because I was doing various extractions of soil to determine where my manganese was located. So you have this total amount of manganese in the soil, and then you can subdivide it into this, or this fraction resides here, and then this fraction held a little bit stronger, it's right here, a little bit stronger, held right here. And I asked this faculty, you know, how do I justify this? You know what he told me? He says, your procedure is operationally defined. In other words, it's nobody's business but yours. All you have to do is be able to justify your procedure in front of your committee. So this is an operational definition of an ionic compound. An ionic compound, if it's melted or if it goes into solution, will conduct an electric current. Right? So let's think about that. Why? Why does it have to be either melted or dissolved? Let's take sodium chlorine, sodium chloride first, right? We've got this network or matrix of sodium and chlorine ions. That's the way it is in your salt crystal, right? You ever spill salt on a table and pull out your magnifying glass and look at it? No, well, I'm just weird that way. Okay, so sometimes I do it on purpose. So you got the salt on the table. Take your magnifying glass and get down really close and look at it. What do you see? Little cubes. Perfect little cubes. Because of the matrix of sodium and chlorine together, they form cubes. Okay. In fact, mineralogists use those crystalline forms and shapes to help classify their the minerals. Calcium chloride. If it's grown into a perfect crystal, it will be shaped like a rhombus, like that. In fact, it's it's tilted that way, plus it's tilted the other way, right? And for that reason, if you get a nice, perfect crystal and lay it down on some newsprint, you will see at least two images of that newsprint, just looking straight at it because of the way the crystal's formed. Well, back to our topic. Okay, so you've got this solid crystal that's shaped like a cube. And try to think in 3 dimensions, right? It's out this way too. So if you put an electrode right, on this side and connect it to that, to a battery, well, that's not, we got to be able to measure it. So let's put a meter in here. Right? Got to be able to measure any flow of electricity. So that's your ammeter. And you apply a charge across that crystal. What's going to happen? You can take a wild guess if you want. There are really only 2 guesses, right? You either get a current or you don't get a current, right? Which is it? Which is it? You don't get a current. Why? In order to get a current through that circuit, you've got to have the charge move. In the wires, sure, electrons will move. But between these electrodes, what's moving? Nothing. These ions are locked in position. They will not move. Okay? The only way they're going to move is if you free them from one another.
If you put
Yep.
water.
Right. Okay. One way is to dissolve it in water. Right. So when you put it in water, what do you have?
Salt water.
Yeah. You have individual ions floating in that water. Now, when you put your electrode in here, well, and your meter, now those ions are free to move. So when they get a kick from one side, from electrons, then that kick is transferred to the ion next to it, and that bumps along and moves the current in the circuit. Same thing can happen if you melt it. If you melt it, now you've got a liquid, and these ions are free to move past one another. Okay? All right. So that is an operational definition for an ionic compound. Either melted or in solution, it will conduct electricity. There's some ionic compounds that won't go into aqueous solution. They're insoluble. So in that case, you have to melt them. Or put them in something that they will dissolve in. Got to get those ions apart before they will conduct a charge. Okay. Anybody need a break? Are y'all good? Like always, you know, if you feel the call of nature, just go ahead. Because everything's recorded. It's going to be posted on Blackboard. So, in fact, I'm hoping you go back and look at it anyway, because it's been my experience that a student taking notes, you only catch about every 3rd word anyway. Right? So it's good to come back and look at it again. I didn't have that advantage when I was a student. We did have voice recording. And I would do that occasionally, and it really helped. Go straight back to your office or your apartment, listen to the recording, get it down before it all fades. Okay, so models, right? We're going to try to bring all this stuff together in models. Right, so what does a model imply? Theory, right? Theory versus what? A law, right? A law just says, this is what happens. I don't know why, it just happens. It happens this way every time, right? If I put these numbers in, I get those numbers out. Or if I do this, This happens every time. That's a law. A theory is 99 times out of 100 accompanied by a model. We try to build either a mental image or a mathematical image of what's happening so that we can take it apart and say, this is why it happened that way. That's the key word, why. Models and theories always imply why. So these are fundamental properties of a model, right? I've mentioned models several times this semester, and I sort of let the particulars try to sink in rather than explain them in detail. First and foremost is a model is not reality. You may already feel that in your gut, but it's good to restate it. Right? A model is not reality. It's like a model battleship or a model airplane that maybe some of us guys used to make. I don't know what, the girls make models? I don't know. Anyway, it's a representation of reality. Right? And it's good to have, because one thing you can do with a model is you can change things in the model and see how it affects the model. Now, if you've got a good model, the effect that your change has on the model will mimic what happens in reality. That's the test of your model, right? And remember what we said, what happens when the model doesn't work, right? Change it, modify it, or throw it out and start over, or restrict its use, right? Once you know its limits, then oftentimes it's just as valuable to restrict its use and know when to use it and when not to use it, right? And we'll encounter some of those types as we move along in this discussion of bonding. Okay, that's first and foremost. Model is not reality. Models are oversimplifications. What do we mean by that? We mean that we have to simplify it in order to construct the model. In other words, we don't know every detail that may be involved in reality. So we try to take the major components of reality and put them into a model. Right? So that takes some intuition. Sometimes, very often, it takes experimentation over long periods of time by many people. And then somebody down the line says, hey, we've got all this information, why don't I bring it together? Synthesis. And make a model that works. Sometimes it does. And generally speaking, especially people who develop the model in the first place, don't like to throw it out. It's like their baby. This is my model. There are many others like it, but this is mine. Right? The Marine Corps with their rifle. This is mine. I'm not going to throw this model out unless somebody forces me to. And some scientists go to their graves believing in their models when everybody around them knows that they're wrong. Right? They just take it to the grave. Maybe that's why it takes so long for us to progress in the sciences. I mean, the old timers have to die off so we can bring in new ideas. But generally speaking, models become more complicated over time. And usually, right before we throw it out, it's just too unwieldy. Right? You've got too many factors to consider, and it's no longer elegant. That's the scientific term for a simple model that explains everything. It's elegant. So after Einstein made a name for himself, with relativity, and actually before that was he explained the photoelectric effect, mathematically speaking. That's what got him his first Nobel Prize. But after he had established himself, he spent the rest of his life working on a grand unified model to bring all these little models together into one model that explained the whole universe. And somebody asked him, why are you wasting your time on that? He says, I can afford to. He probably did in German. I can afford to. I've already made a name for myself. I've got my small fortune I can live on, stipend, whatever. See, these young guys, I mean, they've got to produce, right? I can spend my time frittering away the hours working on this model. So the models become more complicated until we throw them out. Or sometimes you can back them down, say, throw that out, throw that out, throw it out. Just use it like this under these conditions. And you always have to, corollary to that is you always have to understand what are the underlying assumptions of your model, right? So that you don't misuse it, right? You can't have a model for a battleship and try to build a plane out of it, right? It just doesn't work. So you have to know what the underlying assumptions are, right? But you know what an assumption is, right? Maybe I asked you that before. Okay. And it's not always bad when a model goes wrong. Right? When an experiment doesn't turn out the way you want, what do you do with it? You try to figure out why it went wrong, right? That can be as valuable as an experiment that went right. For one thing, it can tell you, don't go that way anymore. It's a waste of time, so you spend your time and money going this way. You go down that way and say, uh-oh, dead end again, back up, down this way. So wrong models, experiments that don't work are not bad. Right. So I told you these earlier, and I'll give you some examples. This is what you do when a model stops working. One of these three things: restrict it, modify it, or throw it out. Like J.J. Thomson's plum pudding model of the atom, right? Just a mixture of positive and negative charges in there. Turned out to be wrong, right? When Rutherford did his gold foil experiment, he proved that the plum pudding model was no good anymore. Thomson accepted that one and went on to do something else. Okay, so we began talking today about what a bond is, and we couched it in terms of the strength of attraction, and that was based upon the energy level of the aggregate, otherwise known as a compound, is lower than the energy level of the individual atoms that go into making the compound. So that difference is the bond energy. Now, if you have a compound with more than one bond in it, this would be bond energies, right? And it would be more difficult to make sense of it, make sense of individual bonds with that much information. So we have to define our experiments and conduct our experiments in such a way that we tease out individual bond energies. That is of more value in the long run, knowing the individual bond energies, because then it turns out these bond energies are fairly consistent with each other for vast numbers of molecules. Like a single bond with an oxygen has a certain amount of energy in that bond. A double bond has a certain amount of energy. Or if you have sulfur and oxygen, it has a different amount of energy. So you gather together all of these individual bond energies, and you can use them to determine what's the energy of the reaction. So that's where I'm headed, right, in this discussion, to determine what is the energy of the reaction. Right, before we get there, the types of bonds, right, I mentioned them earlier. Let's just reiterate. If we have a single line between two atoms, that's a single bond. How many electrons is it? Right, 2. Right, divide symbol. Right, 4 electrons? 6 electrons, right? I don't know of any 4s, so we'll stop at 3. Triple bond. Now, there's another characteristic that we also notice about these bonds. The bond length. The bond length decreases as we add bonds, right? So the strength of the bond increases and we draw those atoms closer together, right? So we would expect that, let's do a series. Try to compare apples and apples. Let's say we have this compound. Those are hydrogens. And we're going to focus on that bond right there between the carbons. Okay? We can also have this one. Right? We ignore the hydrogens. We're focused on these bonds right here. And then the last one in the series, there. Anybody have a cutting torch at home?
Yeah.
Acetylene.
Yeah.
That's acetylene. Okay. Just add oxygen to it at the proper rate and the proportion. And don't blow yourself up. And you can cut through most things. Okay, so we've got single, double, triple. So what happens to the bond length here and the bond strength? The bond length decreases this direction. And the bond strength increases as well. Right? So you're essentially storing more energy in there. So when we combine these with oxygen, per mole, we should get more energy out of that one than we do out of this one. Okay, so this table comes straight out of your textbook, and it gives you the enthalpies for these bonds. So hydrogen is 432, and I left out the units. I think they're kilocalories per mole. Don't hold me to that. You look it up in your book. I'll probably give you more information than I've given you there. But as long as we know the energies of these bonds, we can use that information to determine the enthalpy of a reaction. Because what happens in a reaction? Well, if you have individual atoms, of course, you just form the bonds. Well, maybe not. Maybe you've got to make ions first, right? So it's probably more complicated than that. But if you know a reaction is going to take place, let's keep it simple. Say methane and oxygen. And we're going to form carbon dioxide and water. Okay, that's typical. Any hydrocarbon with oxygen is going to make carbon dioxide and water if it's a complete combustion. Now, it's not inside your automobile engine. That's incomplete combustion. That's why you have a catalytic converter. That's to fix the mess that's coming out of your tailpipe. But if we go to completion, then we have, let's see. I think that's balanced. What we have to do, in a theoretical sense anyway, is we've got to break these bonds, right? Break those carbon-hydrogen bonds. We got to break this oxygen double bond, in fact, 2 of them. Then we can form 2 carbon-oxygen bonds, right? So we break these bonds, we form those, and we form these single bonds, 2 of them, right? So we need 2 of those. And we need 2 of these. Right. So we're going to add energy in here and get energy back there. So if you take the energy of the bonds here for each of these, add them up, right? 2 times each one of these, and then subtract the energy that you had to put in to get there, then you should be able to find out what is the overall enthalpy of that reaction. Right? So this would be the endothermic process, breaking the bonds, and the exothermic process, getting your energy back when the bonds form. And this is what it looks like, right? In fact, that should be in your review document in the back of your review document. Let's check to be sure. In useful information. Yep, it's almost at the bottom. So here's the sum of your bond energies broken. Following formula. I must have said that backwards. Bond energies formed. Okay. I'm thinking of something else. So this is broken and formed. So you take this one minus that one. Okay.
Okay, so from,
Question?
okay, yeah, question. Okay, so the average bond energies where it has like H bonds with hydrogen bonds with hydrogen, it gives you a 432 number. 432.
Where it has this one and then 432?
Now, how did they find
That's a good question, and I don't know exactly, but it should be fairly easy with this one, right? Because all you have to do is already a gas, dihydrogen.
Yeah.
And all you need is how much energy does it take to break that bond, right? So they just put enough energy into it until they've got individual atoms, and however much energy to put. That's the easy one. Some of those others are a little more complicated. They're probably derived. They take reactions. Once you start building up a data set with these easy ones, and sometimes you can use the easy ones to help you deduce the more difficult ones. So let me say it again, because I said it wrong the first time. The energy required to break the bonds minus the energy that of the bonds formed is your delta H. And notice all of those energies are positive numbers. Right? Those are the energies required to break those bonds. That means they're endothermic. They're all endothermic. That's probably why this is bonds broken minus bonds formed, because they're all positive. Now, if you get more energy back than you put in, what delta H sign do you have? Negative, right? So it's exothermic. You get more energy back than you put in. And that should be the case here, because we know when we burn methane in the lab, right, in our Bunsen burner, it gets hot, right? It's exothermic. Okay, so the other trick, well, one of the tricks to simplify the process is to recognize when you have a different bond on the product side and when you don't, right? So look here. I have to give you some instruction on convention. When we write this in a molecule like this, like that, these hydrogens are connected to that carbon, like that. And then the carbon is connected to the nitrogen with a single bond. All right, that's a convention that's not explained there. So if we have this one, and we're going to make this one, which bonds do we really need to be concerned about? Just these two. Well, actually, no, not just those two, because this one is that, and this one is that. So I should have said it this way. Which ones can we ignore? The carbon hydrogens, right? You know, you can save yourself some calculations. It doesn't matter because the energy on this side is going to be balanced by that energy. You really only need to focus on this one and that one and that one. So add these two together, subtract those two, and you can save yourself that much headache. So as it turns out, this process is exothermic, right? Going from this one to this one. Okay, now we're going to get to some real models. The first one that really started to explain things well is called the Localized Electron model. And if you take the name apart, like I like to do, then we're focusing on the electrons. Of course, that makes sense if this is a bonding model. Focus on the electrons. And the electrons are localized. What does that mean? That means, yeah, say?
How they're in one place.
Halfway there. They're all in one place around a particular atom. They continue to be assigned to that atom even during the bonding process. That's the localized electron model. They start off with hydrogen here and with carbon there, then we keep them with these two as they intermingle and form the bond. Okay. Now there's coming up is what we would call it, is a model underneath the model. Didn't think that could happen, maybe. Should have known better. When we have to, we complicate things. Localized electron model, then within the localized electron model is a submodel. And we'll get to it in a minute. Okay, so these atoms in the molecule are bound together by sharing their electrons in pairs. And the key here is that they use their own individual atomic orbitals to do that. So if one has an s orbital and the other one has a p orbital, they overlap and form the bond. But you still have p orbital and s orbital, right? Okay, so when we describe this model, first of all, besides being localized around a particular atom, there are two different types of electrons. Those that are involved in bonds and those that are not, right? And now when we start talking about these lone pairs and bonding pairs, right? The bonding pairs are the ones that are between the atoms. And the lone pairs would be, well, let's use a different one here. Let's use nitrogen. The lone pairs, they're not bonded to anything. When we start talking about these bonding pairs and lone pairs, we're talking about valence electrons only. Those that are out there available to bond, right? So with the larger atoms, we have some core electrons that aren't involved at all. Just the valence electrons, those in the outer shell, and for convenience, those that are in the octet, or potentially in an octet. Right? So if we bond nitrogen with nitrogen to make the gas, the inert gas that you breathe, we have these 1, 2, 3 bonding pairs and 1, 2 lone pairs. that are not bonded. Okay, we need to keep track of those lone pairs because we need them for the next steps that we're going to encounter. All right, so just a heads up, in this chapter, we're only going to be concerned with this part and this part 1 and 2. We're going to stop there with chapter 8. And chapter 9 is going to carry on with these other concepts. Okay. All right. So, a chemist by the name of Lewis, G.M. Lewis, his initials were, came up with this convenient way of representing atoms as they form their bonds under this localized electron model. And it's called the Lewis structure. And it's based upon the octet. So when we draw the atom, we want to put electrons around that atom before it bonds in such a way that we have an idea of how it's going to interact with other atoms. Right? So we look at carbon and we say, how many valence electrons does it have? Well, we got to stay in the same period. Right? So it has 1, 2, 3, 4 valence electrons. Okay. That's the way Lewis would write it. 4 valence electrons, and we start wherever you want to and go clockwise or counterclockwise, doesn't matter. But you put 1 in first before you start pairing them up. Okay? So if we had neon, and neon, of course, is not going to react, but just to illustrate the point, how many valence electrons does it have? It has an octet, right? Right, so we go 1, 2, 3, 4, 5, 6, 7, 8. And that shows us that neon has a complete octet, 2, 4, 6, 8. It's not going to bond with anything. One more. How about chlorine? Right? How many valence does chlorine have? Well, start over there. 1, 2, 3, 4, 5, 6, 7. So we go 1, 2, 3, 4, 5, 6, 7. That leaves this unpaired electron available for reaction. Okay. So here we're making a point of the Duet Rule, right? Hydrogen is strange in that way. It's Lewis. The Lewis structure for hydrogen is just that. That's it. It only has 1 electron. So when it comes together with another hydrogen, now they have 2 electrons. There's your bond. Right? So whenever you have 2 electrons and they form a bond, rather than leave them in there like that, I always convert them to a line. That, for convenience sake and help keep me from making mistakes, is when I have a line, I know that's a bond. You know, I don't have to count, where is it? Between 2 atoms, okay, that's a bond. If I make a line out of it, I know it's a bond just at a glance. Fluorine, single covalent bond. There's your double bonds. Let's get on to drawing Lewis structures. Okay. So I showed you Lewis structures for atoms. You can also do Lewis structures for compounds. So if you have a compound that you know is going to be 1 carbon and 2 oxygens, and what you do is you add up all the valence electrons available. Right? So carbon has 4, oxygen has what, 6? 6. So that's 16 electrons total in the valence shells. Now you start This is all in words up there, but I think it's better to show you an example. Then the words will make more sense. Generally speaking, the more electronegative atom is going to be toward the center. Yeah, that's right. Except in this case, we know the carbon's in the middle. So we put it in the middle. But once you've got that arrangement, you start from the outside and work your way in. So we got 16. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Wait, that's water. Come on. Oh, I'm sorry. Start over again. Well, we can use 16. Why am I starting over? Because I skipped a step. I should have seen that one coming. Okay. Back up. Count your electrons. That's true. We got that right. Then form one bond to hold the whole thing together to begin with. 2, 4. Now we have 12 electrons left over. Okay, now I can start putting them. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay. Now all of our electrons are placed in the molecule. But everybody doesn't have an octet, right? So we need to make an octet somehow or other. These 2, 4, 6, 8. Oxygen's got an octet. It's good. Carbon doesn't. 2, 4. So we need to move 2 of these electrons here, make a bond. 2 of these electrons here, make a bond. So now we have 2, 4, 6, 8. 2, 4, 6, 8. And 2, 4, 6, 8. Now we've got our octets. Okay? So that's how you draw the Lewis structure for carbon dioxide. Did I lose anybody? Probably ought to do another one. How are we doing on time? 12 o'clock? We're going to run out of time, I think.
Lewis structure.
Okay. Say again?
Well, you want the time?
Yeah.
Well,
We go till
12:20.
12:20. Okay. If we run out of time, I've done this before, haven't I? Run out of time.
Keep on recording.
I'll keep on recording, or if a class is coming in, if my next class comes in too soon, I'll stop this one and pick it up after that class is gone. But it will be posted on Blackboard to finish out, so that we don't rush through this stuff too fast. Okay. So these are examples. Yes?
This is just me earlier. The only reason why you took out those dots and made them into the bond line was because to get 8 total dots.
Yes, to make the octet.
Yeah.
Right. And we want to be sure that you don't destroy the octet in the ones that are already there. So by moving those 2 electrons from either side into the bond position, they're still available for the oxygens, but they're also available for the carbon to make the octet. So you just circle the atom, count around it, and be sure you still got an octet around that individual atom. Okay. Let's see. Draw a Lewis structure for each of the following. How about, those are too simple. Let's get some more complicated ones. How about ammonia? So we've got ammonia. All right, so how many valence electrons do we have? Ammonia is, nitrogen's 5. Hydrogen is 1 each, right? So we have 3. That's 8 electrons. Okay, so nitrogen's going to go in the middle. Then we're going to form a bond with each one of the hydrogens. 2, 4, 6. So we got 2 electrons left. Where are those 2 electrons going to go? Work from the outside in. No room there, no room there, no room there, right? Hydrogen can only have 2. So we got to put the 2 on the nitrogen. That's why it has a lone pair. Okay. Now, sometimes the octet rule doesn't work. Boron trihydride is one of those. For these, you have boron's only got 3 electrons, so 3 plus 3 is 6. And when you form the 3 bonds with the hydrogens, you use them all up, right? We don't have an octet. So you just live with it. It's one of the flaws of this model that we just deal with. Sometimes you have more than an octet. Right? So in this case, you've got 34 electrons, and we placed them all around the fluorines, and sulfur's got its octet already, but we've got 2 electrons left over. Where do they go? They go on the central atom. Yeah. Yes?
So does the position in the central atom not matter?
Say that again?
The position of the dots, do they not matter in the central?
No, just put them somewhere. Yeah, just put them somewhere. Right, this is a model, right? This is not reality. Right, so you just be sure that they're, and this is the localized electron model, so they have to be assigned to one of the atoms somehow or other. They got to be there. So we put them on an atom. This one has all it's exceeded its octet in the bonds themselves. Right, so they don't always have to be lone pairs to exceed the octet. And one thing you'll notice is when the octet is exceeded, where do you find, in this case, the central atoms? Sulfur, and arsenic. Right? Arsenic has available to it 3 Ds. And 3S, 3P, 3Ds are also available to sulfur. Right? That energy level is still there. It just didn't have any. Sulfur by itself didn't have room for, it didn't have a need for the Ds. But when you start making compounds with it, yeah, it can use the Ds. Right? So when you find exceeding octets, it usually happens from here down. You won't exceed an octet up here. You might be less than an octet. But down here, very often you will exceed an octet. Okay. So let's see, let's try this one. What's the name of that one? Type 1, type 2, type 3. Where does it come from? Phosphorus, chlorine. They're both nonmetals, right? Yeah, type 3. So we just have to say what it is. So it's phosphorus. What's the prefix for 5? Pentachloride. Okay, now to the, that was just a side. Phosphorus, pentachloride. So how many in phosphorus?
6.
How about 5?
Oh, 5, sorry.
And chlorine is 7 each. 7 times 5 is 35. So we have 40 electrons to deal with. Phosphorus is going to be in the middle. We got 1, 2, 3, 4, 5. 2, 4, 6, 8, 10. So we have 30 electrons that we have to place. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10.
6 on each one, wasn't
Yeah, 6 on each one. Save us some
it?
time.
5 times 6, 36.
Yep. And they're all used up. So now we've exceeded the octet, 2, 4, 6, 8, 10. There's 10 on phosphorus. And look where phosphorus is. In the third period, it has access to 3 Ds. Okay, this is just a review. And this makes mention here of the exceeding octets, making use of d orbitals to do it. And that's one of the first chinks in its armor of the localized electron model. Those chinks come from not satisfying the octet or exceeding the octet. That's problem number 1. Okay. Now, what is a valid Lewis dot structure? Well, if you draw it the way we've been drawing it, and you make sure that each of your atoms has an octet, right? 2, 4, 6, 8, 2, 4, 6, 8, 2, 4, 6, 8, 2, 4, 6, 8. That's a valid Lewis dot structure. But what if we move that double bond over here and put one of those lone pairs over there? That would also be a valid Lewis structure, as would this one. So what do? By the way, this is the nitrate ion, right? Remember your polyatomics? That's one of your polyatomics, nitrate ion. Well, this is a case where the model just kind of slips. Doesn't fall down completely, but it slips on the ice. And the fix for it is called hybridization. So we say, all right, the reality is it's a hybrid of these 3 because they're all valid structures. So what they're doing is they're rapidly changing back and forth so that you really can't tell which one's which. Now, we have to do this. This is the only valid fix because with the localized electron model, those bonds and those lone pairs have to be assigned to atoms, right? They can't be placed anywhere else. So when we have 3 valid Lewis dot structures, we've got to not hybridize them, excuse me. This is called resonance. They resonate among those 3. We'll get to hybrid later, sorry. Okay. Let's see, there's more practice doing dot structures. And remember, whenever you have a charge on the ion, don't throw it away, right? When you draw your Lewis dot structure, add that electron in there with the rest of them, okay? So the total here would be 6 plus 4 is 10 plus 5 is 15 plus 1 is 16. So you start off with 16 electrons here, okay? Now, what's a formal charge? We got 4 minutes. Remember when we talked about oxidation states? The oxidation state of an ion is the charge on the ion. So the oxidation state on sodium would be +1. Oxidation state on chloride ion would be -1. That works for a lot of things. But when we start talking about covalent compounds, they don't have charges. Right? So a more useful way of describing where the electrons are and how to decide which is the best Lewis dot structure, because you can draw lots of different Lewis structures for some compounds. Best way to figure out which one is the best one is to look at the formal charges. Now, we say charge, but it's not really a charge. Formal charge just means on paper. So how do you determine the formal charge? Well, by definition, you take the number of valence electrons on all the free atoms. Well, actually, you take let's use an example. Carbon dioxide. Okay, what would be the formal charge on each one of these? Well, you say, what are the valence electrons of the free atom? This one has 4, and these have 6. Okay. Then you look at, let's see, I left off some, sorry. There you go, lone pairs. Then you say, how many electrons are actually on that atom? Right. So when you come to a bond, they only get half. Right. So for each one of these bonds, it gets 1. So there's 1, 2, 3, 4, 5, 6. There's 1, 2, 3, 4. There's 1, 2, 3, 4, 5, 6. And then you subtract. You subtract this one from that one, and in each case we get 0. Right. So the formal charge on carbon is 0, on oxygen 0, and on that oxygen 0. And what you do is, if you have several Lewis dot structures to choose from, you pick the one that has the lowest aggregate number. Right? If we had come out with -1 here and +1 here, we would not prefer that one to the previous one. The previous one would have been a better choice. So that's the utility of the formal charge. So you've got some problems to work in. It'll give you some practice working the formal charges. But that's the way you produce the formal charge. And here's the formula. The valence electrons, well, these are the valence electrons assigned to an atom, right? If you've got lone pairs, that atom gets them all. If it's a bond, it gets half. Okay, so I better mark off where we stop so I can pick up the recording at the proper time. Let's see. Rules governing formal charge. Here it is. For my benefit. Okay. My apologies. Next week, we'll do a review and we'll go in the lab and do, I guess it's our last lab. Next to the last lab. Yeah, I can bring it with me. We'll do this lab for sure. The molar mass of a volatile compound. Okay, it's fun. You'll like it. Calculations are real simple. Yes. Let me stop this so it'll be converted. Okay. Now these are the general rules for formal charge calculation And we just went through them as an example, practice example of calculating the formal charge. So let's do one where it doesn't turn out so pretty. How about this one? So if we have, first thing you do, let's start from scratch. We have this compound, POCl3. Draw the Lewis dot structure, right? So phosphorus is 5 electrons, oxygen is 6, chlorine is 7 times 3 is 21. So that's 27, and 5 is 32. So we have 32 electrons we have to place. In this case, I'm just going to tell you, phosphorus is in the middle. So we have 32 electrons. Phosphorus goes in the middle, then we have oxygen and the 3 chlorines. So that's 2, 4, 6, 8. Right, so now we have 24 electrons left over. So we start from the outside and work our way in. So 1, 2, 3, 4. 4 times 6 would be 24. So we could put all of them like this. And that would give everybody an octet. 2, 4, 6, 8. 2, 4, 6, 8. 2, 4, 6, 8. 2, 4, 6, 8. And phosphorus would have 2, 4, 6, 8. So we've satisfied the octet rule for this compound. Now, let's see what the formal charge is to help us decide if this is a good or a bad Lewis dot structure. So, how many electrons for each one? Well, we just did it before. Valence electrons for oxygen are 6. And then we subtract how many that it's given. 1, 2, 3, 4, 5, 6, 7. 1 for that bond. So it has a -1 formal charge. How about the chlorines? The chlorines look like they're all the same. So if we do 1, we've got them all. So chlorine is 7 electrons minus how many? 1, 2, 3, 4, 5, 6, 7. Each one is 7. Formal charge on all the chlorines is 0. How about phosphorus? Okay, phosphorus starts out with 5 valence electrons. And how many does it have now? 1, 2, 3, 4. Right? 1 for each bond. Right? We have to share. So that's +1. So in this case, the chlorines are formal charge 0, oxygen is -1, and phosphorus is +1. That's not too bad, really. I've seen much, much worse. And really, I don't see any other way to write this compound with a Lewis dot structure. Now, what do we do with these formal charges to be sure that we're not making a huge mistake? Well, the other rule is you take each of the formal charges, 1 for oxygen, +1 for phosphorus, and then 0 for each of the chlorines. Add them together, and they have to be equal to the charge on the compound. If the compound is neutral, they have to be 0. And in this case, they are. So we're safe there. It's kind of like doing balancing your checkbook, right? How do you balance your checkbook? Well, if you write a check, you subtract that from your running total. How do you know that your subtraction was correct? You add it back to the number you got and see if it's the number you came from, right? It's a check on your system to see if you've made any mistakes in calculating your formal charges. So here's a concoction of carbon dioxide. We determined this one to be formal charge of 0, 0, 0. Did we not? Okay. What would the formal charge on this one be? If we claim that this one is a valid Lewis dot structure. All right. Carbon is going to be 4 minus 1, 2, 3, 4 equals 0. Carbon's okay. How about this oxygen? 6, right? Minus 1, 2, 3, 4, 5, 6, 7. Minus 1. Okay. How about this one? 6 minus what? 1, 2, 3, 4, 5 equals plus 1. So in this model, we've got plus 1, 0, minus 1 versus 0, 0, 0. Which one's better? That one. It has the lowest aggregate formal charge of all of the atoms in the compound. So we go for this one. I don't know if it's proper English, but this one's more valid than that one. So here's one mistake that you don't want to make. When we calculate formal charge, do not assume that that formal charge is an actual charge on the atom. It is not. It is simply a bookkeeping method for keeping track of the balance of electrons in our compound. All right. So here's that this subset model that I was mentioning earlier. This Vsepr model is within the localized electron model. In other words, you have to generate whatever consequences fall from the localized electron model, the Lewis dot structure, check your formal charge to be sure that you've got the lowest aggregate formal charge. Then, once you've got that Lewis dot structure that you've selected, you can use the Vsepr model to determine what is the most likely geometric arrangement of the atoms. Okay. Vsepr stands for valence shell electron pair repulsion. Okay, Vsepr. Now this is a slight misnomer because while the valence shell electrons are true and the repulsion is true, we don't always talk about these repulsions in terms of pairs of electrons. More accurately, it should be valence share electron group repulsion, VSEGR. But the name stuck and we can't change it. Not easily anyway. So what's the idea here? Once you draw your Lewis dot structure, the electrons in lone pair status and in bonding pairs or bonding groups for double bonds, triple bonds, bonding groups, they try to get as far away from each other as possible. So that's the repulsion part. And by repelling each other as far as possible, we can deduce from that repulsion what's the most stable geometric form of that molecule. Okay, we need some examples. So what are the possible, first of all, what are the possible geometric arrangements that we could have? Well, you can have a linear molecule. Every atom in the molecule is in a straight line. Okay, that's possible. Or you could have trigonoplanar, that is, you've got a central atom and 3 atoms around it, and they're equally spaced. So if you connect all the dots, let's see, this would be an example of a linear. Right, straight line. Trigonoplanar would be something like boron trihydride, right? In a perfect, if you look at the triangle, there's your triangle. Those are not bonds, that's just showing the triangle. Okay? What else? Well, if you have 4 spaced around it, you can have a tetrahedral. Methane or carbon tetrachloride would be a good example there. And it forms this perfect 4-sided geometric form. That's a tetrahedron. Okay, those are just examples of the lowest order examples: linear, trigonoplanar, tetrahedral. Now we need to look at actually how we use the Vsepr model. First, you need the Lewis dot structure. That's key. You have to draw that Lewis dot structure. Then you count the number of bond groups and lone pairs around the central atom. The key to this Vsepr model is that you can have different geometric shapes in the same molecule. Like if you have a huge molecule, you could have maybe a tetrahedron over here, you could have a linear here, you could have a trigonoplanar here. So it's all based upon a central atom and what's the shape around that central atom. But in the beginning, we're going to take individual molecules to flesh out the process of using the Vsepr model. All right, those are your instructions in order. It would be better if we just work it out. Right. So how about hydrogen cyanide? Oops. Hydrogen cyanide. Well, this one has 1 electron, 4 electrons, and 5 electrons. So that's 10, right? So 10 electrons, carbon in the middle, nitrogen, hydrogen. So that's 2, 4. So we got 10 minus 4 is 6. So we have hydrogen can't hold anymore. So work our outside in. 1, 2, 3, 4, 5, 6. All used up. But we don't have an octet on carbon yet. So how do we get an octet on carbon without destroying the octet for nitrogen? If we move these 2 in here, like that, then we have this, this, and that. Now let's see, do we still have 10 electrons here? 2, 4, 6, 8, 10. And we have a duet here. We have an octet here. and we have an octet here. So that is our valid Lewis dot structure. Now, what's the shape of this molecule? The shape depends upon the central atom. How many groups and lone pairs are associated with that central atom? In this case, we have 1, 2 groups. That's it. Okay. You might see 3 bonds there, but for the VSEPR model, we need to count these as 1 and those as 1. So we're going to say for 2 groups, the geometry is linear, right? And what's the bond angle around with this carbon as the central, right? So if it's central, what kind of angle is it from that side to the other side of the linear? 180 degrees. Okay? We can work out these others. pH 3, we have to prove that pH 3 is actually this. 1, 2, 3. 3 groups, trigonal, planar. What are the angles? Right? Remember the angles, the internal angles of an equilateral triangle, right? That. We have to go 360 degrees, get all the way around. So each of these angles is 360 divided by 3, which is 120 degrees. SF4 is what? Well, SF4 is a weird one. Yeah, SM4 is a weird one. Let's see if that gets it. Sulfur, chlorine 1, 2, 3, 4. 4 times 7 is 28. Sulfur is 6, 34. So it's 4 times 6 is 24. Is 10 left over. So 1, 2, 3, 4 is 6. Like that. Hold sulfur tetrafluoride for a while. It's too weird to handle right now. Let's do oxygen. Water. Let's do it like this. Okay, H2O, right? So there are 2 electrons there, 1 for each hydrogen, 6 here, so that means we have 8. So now we have oxygen and hydrogen. So that's 2, 4. Okay. So we need 4 electrons. Where do they go? Can't go on the hydrogens, they have to go on the oxygen. 2, 4, 6, 8. So that's the beginning Lewis dot structure for hydrogen, water. But if we have, how many electron groups do we have? We have 1, 2 lone pairs and 2 bonding pairs, so that's 4. 4 of those is tetrahedral. Okay? And what's the bond angle in a tetrahedron? 109.5 degrees. All right. Now I've got to make a distinction between electronic configuration, electronic geometry, and molecular geometry. There's a difference. If, in some cases, you have lone pairs that cause the shape of the molecule to change. In this case, you do. Because what would a tetrahedron look like? With oxygen in the middle, then we would have maybe hydrogen here, we have a lone pair back here, lone pair up here. Right? So what we've got is these two hydrogens out here, and those two lone pairs back there. So another way to draw that is like this. The oxygen molecule is, the water molecule is bent because the tetrahedron is true for electronic geometry, but molecular geometry, we only consider the atoms, and that makes it bent. How about this one? A molecule that has polar bonds will always be polar. Is that true or false? Remember what I said? Things that have to happen. If you have a polar molecule, you have to have polar bonds first. That's true. But what happens if the dipole moment of all the bonds cancel one another out? Then you have a nonpolar molecule. So it's not always true that with polar bonds you have a polar molecule. Carbon dioxide is a perfect example. If we draw carbon dioxide, we get that. All right. There are several pages left in this discussion that describe the geometries, both electronic and geometric, or molecular, electronic or molecular geometries. And I'm going to leave that for you to look at the examples in the PowerPoint printouts that I gave you. And we'll discuss those during the during our examination and review next week. I think it would be best to hold it till then, till you had a chance to look at the particulars of this method and then bring your questions to class. Then the questioning and the answering should clear up any problems that you have. And you can always contact me by phone, by email. If you have a problem that's just really burning you and you can't sleep, then I'll try to figure it out for you over the telephone, or we could set up a Zoom session, whatever's required. Or if you're in the neighborhood, stop by my office, and I think we can clear up any questions you have pretty quick. But for now, I'm going to have to cut this lecture off because I got another class coming. And we'll see you next week.